we are 5. Let's see how many will do it until tomorrow. Okay, today's topic is sorption. Good morning. And you see here some products which can be dried. Maybe you are mostly acquainted here with stable crops here. This is maize. You see it here in the field, and here the kernel after drying, and there is not that much a difference between the fresh one and the dried ones, because grain is harvested quite dry in the field, depends on the weather conditions, and then you dry it down to a final moisture content, and we learn today how to find the target moisture content. But you see also other crops, which I would also call high value crops, which needs a lot of investment in producing it, and they also have a much higher price than stable crops. Like here fruit, I just put here apricot. I think also here in Costa Rica, you know apricots, dried apricots. The next are mushrooms here, fresh ones and dried ones, and maybe more mushrooms are even sold in dried form than in fresh form, at least in Europe. Very common to have it in the shelf. Or here, medicinal and aromatic plants, like the teas we have, chamomile, peppermint, lavandula, and all those nice herbs. And I think some of them are also here in Costa Rica. At least I could find peppermint tea in the market. Is peppermint grown here? Okay. Chamomile grown? Okay. So you're very acquainted with that. And there is a big difference between the fresh ones and the dried ones, because they have a high moisture content, 80% and more. And after drying, they are around 10 or below % moisture content. So what's happening when the material are not dried properly and stored in too high moisture content? That's what we see here. You see nice maize kernels, and on the right hand, some which are rotten by microbial growth, which will start when the atmosphere in the storage system is too high. And that's the topic of today, to decide when the atmosphere in a storage system is dry enough so that microbes cannot develop and that we have safe food. This is an extreme example to see something, and there are also microbes before you see it. By the way, everywhere are microbes, but bad ones, aflatoxins, created by Aspergillus flavus, for example. Good morning. And this could be Aspergillus flavus, for example, here, producing those black spots. And those fungi also produce toxins, the mycotoxins, and this is really a problem because you cannot see it easily unless you have those extreme conditions, and it's accumulated in the food chain. So maize, we have learned on Monday, is mainly fed to animals, and then aflatoxins are accumulated in milk and meat in the food chain, and they are cancerogenous and really a severe problem. By the way, Catalina coming now, or is already in Germany, will work on this problem, so mycotoxins on maize. Fine, this is the background of our topic today, the problem which we have to solve, and again, we need some fundamentals. And first, maybe the form of moisture in agricultural products. So moisture content is all liquid water with nutrients which are diluted in the cells and in the veins. So it's not pure water. There are substances, dissolved starch and sugar, but we call it therefore moisture. It's not H2O. It's not pure water. Water vapor in the pores is also water, the vapor. And you have here such a structure, such maybe a leaf of a plant. And you have here different cells here, and in between the cells there are spaces, there are pores, and those pores are filled with air and water. And there's also an exchange to environment via stomata. Here is such a stomata, such an opening, and air and water vapor can be exchanged here. And also some veins here, and in the xylem here we have water flow, and in the phloem we have sap flow in a plant. You see that water is there in different forms in the plant. And in a fresh plant, plenty of it, around 80% is water. But the water is differently bound in the plant material, and I have here a list. It might be free water or free moisture, and this is on the surface. After rain, you have water on the surface, and plants are even pushing out water, guttation. You can see it on a meadow in the morning, that there might be droplets on top of the stalks. Is this also occurring here in Costa Rica? So this water is really expelled by the plants. Fine drops on grass, for example. Or if you cut a product like a potato, if you go to dry potato and you cut slices, then on the surface you have water. And this I would call here free moisture. Then we have capillary moisture. This is moisture here in those capillaries here, all over. And we have osmotic moisture, so moisture which is bound to substances like sugar and starch. It's bound because there are osmotic forces from those dilutions. And we have chemical bound moisture. This is incorporated in the molecules. So you see different ways how water can be bound in a product, and if you should make a ranking here, which bounds are most strongest, what would you say? What would be the ranking here in this list? Which water is bound very strongly and which water is not so strongly bound? I agree, chemically very strong bound. Very good. Here between the two it depends. Capillary and osmotic depends on the circumstances in capillaries. There's a difference between the capillaries, big ones and small ones, the diameter, and in which diameter the water is more bound, in the big capillaries, the very strong ones, or the fine capillaries, the very weak ones. Where is water more bound? In which kind of capillaries? In the small ones. Yeah, very good. Maybe you remember school time with two capillaries in a water bath, the fine one, and the column was higher than the other one in the thick one. That's the effect. The capillaries by surface tension are binding the water, and in the osmotic moisture is bound to, let's say, sugar and starch, and this depends on the concentration of sugar and starch. And so we cannot decide in between this, but we can decide here free moisture is not very much bound. You even can maybe mechanically push it away, the first part of it, by shaking. Okay, so we see there are different bounds of water here, and the chemical bounds are just broken when the molecules are broken down. Then this water can be set free. Okay, so we need a unit for moisture content, and here we have the moisture content MC wet base, and this is the mass of water related to the total mass, which is the mass of water plus the dry matter. This is not very complicated, a very easy thing, but there are two definitions. The other one here is the moisture content dry base. And this is just the mass of water related to the dry matter. And scientifically, we clearly would prefer this one. But in practice, there is the other one. When we talk about moisture content with a farmer or with a salesman or whatsoever here, those people speak and think in moisture content wet base, and therefore we always have to convert. In science, we don't like it so much because this is not a constant, because the water is removed. And then we don't have a constant base in our calculations. Not very nice. Okay, so always look what is meant, moisture content, wet base or dry base. Normally we give this in percent, and at least in Germany we give this as a dimensionless figure. It's dimensionless, but our colleagues in the US and so, they also convert this in percent. And then the distinction gets lost. And the bad thing is that we have much more water in most cases than dry matter, can be factor 10, and then you have 1000%. Funny unit, huh? 1000% water. Okay, but that's how it is convention. Okay, and you will see later on in our, we will work with the publication, there's also a mix, with and without percent in one publication. Okay. So these two measures can be transferred one in the other. Yeah, there are two very helpful equations here to make dry base moisture from wet base moisture or wet base moisture from dry base moisture. And the relation is not linear. We have this correlation here between moisture content dry base and moisture content wet base. It's not a linear relation. Here, close to 0, yeah, it's very close to a linear relation, and this makes it even more tricky because you think, oh yeah, just can convert it one by one, one to the other. It's not right. If you come higher up here, there's a large difference between the two. Yeah, 60% here is, for example, here 1.5. Yeah, in percent it would be 15%. Okay. 150%. So, okay, how do we determine the moisture content? Okay, there are different ways, and therefore there are certain standards. So if you do this in the lab, you should follow a certain standard precisely, choose one and use this one consequently. For example, as a German standard here, if you measure the moisture content of wheat, you put it in an oven here by 131.5 degrees centigrade, plus minus 1.5. What does it mean? That you should be sure to be above 130. Okay, for 2 hours, and also the particle size is prescribed, smaller than 1.7 millimeters, so you have to grind it and then put it in the oven. Or another standard, ICC standard for maize kernels, and they give it here 130, 233, yeah, for 38 hours. There's a difference, 2 or 38. Or more general for food, according Matisek here, 103 plus minus 2, and this should make sure that you are above 100 for 3 to 6 hours. Okay, so there's a big variety, and therefore my recommendation, okay, choose one and use it. Okay, there are disadvantages to do this in the oven because you also can lose some volatile components which are not water. For cereals, this is not a big issue, but think of peppermint. Peppermint can have 3 or 4% of essential oil, and this is gone. And this is counted as water. Wow, not very good. And okay, therefore there are also other methods. For example, here this Carl Fischer titration. This is Mr. Carl Fischer. And he invented and applied this method to do this by titration. You see here a titration apparatus, yeah, and by this iodine pyridine method here, you can see here a change in color, and meanwhile you measure this inside by electrodes here, and it's just a titration to find the water in a product, and this is very specific to water, just to water. This is really the gold standard. Then you really know, okay, this is the water in my product, nothing else. But expensive, time consuming and expensive. You need here the chemicals which you have to pay, and therefore you cannot afford to measure all the products in everyday life here by Carl Fischer. This is something for science. And therefore we have those so-called convention methods, the oven methods. yeah, at 130 degree or 103 degree, whatsoever your standard tells you. Okay. So we have initial moisture content of the product. This depends, of course, of the plant itself and the maturity stage. So grains are drying in the field. That's the sense of nature, that grains are self-conserving. They are drying down, to be prepared for the next season to germinate again. But not so for fruits. They are fresh, high moisture content. Okay, and we have a certain final moisture content, and this is very important to know. What is my target moisture content? How deep I have to dry down my material for a safe storage? Let's see. We see here different products, starting with wheat, going down to tea and tobacco, and we see typical initial moisture contents, and we see here also recommended final moisture contents. When we go through a bit, wheat initial moisture content 20%, can be higher, also can be lower. This year we have had a very dry summer in Germany. We could harvest our grain even below the recommended final moisture content, which is 14. Corn has a higher moisture content at harvest, at least in Middle Europe, 30 to 35. Do you have any experience with corn, with maize in Costa Rica? Typical moisture contents at harvest? Okay. For himself, subsistence. Okay. They are a large corn producer in the US, selling to the entire world. Okay. Yes, but typically corn here is harvested at a bit higher moisture contents, and you see you have to dry it down to 14. That's quite a bit. Rice, 20, I even would say to 30% moisture content at harvest. Otherwise, rice will scatter in the field. You will lose the kernels. You have to harvest it half green, and then you have to dry it down. Here I have arranged 12 to 14%, always wet base here. Soybeans, quite high moisture content, and then extremely potato, of course, 80%, cassava 60%, and again drying down to around 12. Fruits, also very wet here, but you see, this can be higher, above 20, the recommended final moisture content. Vegetable 4 to 10, can be even lower here. Coffee 12, medicinal plants around 10, tea 3, and tobacco 20. So you see a huge variety of recommended final moisture contents. There is a little bit of rule. If you watch here, these figures here, they are quite similar here also to those here. What can be the reason that there are certain groups of moisture contents which are required, in contrast to fruit, which can be here higher than 20? What could be the reason? So what would you say is a major difference in terms of ingredients between cereals and fruit? Fruit like apples, banana, What is the main ingredient of cereals? Yeah, the duration of the storage also plays a role. But here the major role, the major reason between maybe fruits and cereal has to do with the main ingredients. The texture of the product. Let's think further. Okay. What are the main ingredients? Why do we grow maize? What is the main ingredient of maize? Yeah, flour, starch. Starch. And in fruits? Sugar. Yeah. That's what I would like to hear. Here, okay, in cereals, starch, in fruit, sugar, and they are different hygroscopic. So sugar is more hygroscopic than starch, holding the water stronger than starch. And this is the reason. And some other crops like medicinal plants, here going down to 10. And tea, what is the main component of those plants? So herbs and tea. They are constructed mainly of water, of course, beside water, the dry matter. What is the dry matter made of in terms of tea? What is in tea? Is there starch? Fiber. That's what I want to hear. There is not much starch, there is not much sugar. Most is fiber. Yeah? Hemicelluloses, cellulosis. Okay, and this is not hygroscopic. Not so much hygroscopic than starch. There is a ranking. Sugar, starch, fiber, and the mix of these components makes here the hygroscopicity of the product and governs here the recommended final moisture content. For tea, it's extremely low, to keep its properties. But if you just would dry down tea to 3% and then leave it in the open without packing, it would suck water again, and it would end up somewhere also at 10. Yeah, and so you see, it's not only here a matter of the ingredients like sugar, starch, and fiber, but also the later purpose, how it's handled later on. This is a technical requirement that we have to dry down tea so much. That's expected from the market. Okay, tea has to be dried down and then packed, best vacuum packed, and then sent, and then it arrives here at this moisture content. Tobacco, the other extreme. Yeah, tobacco should stay smooth. Yeah, at 20% here, it will not rot so easily because it's full of secondary substances like nicotine. Yeah, so it's somehow self-conserving. Okay, to make this long story short, the ingredients are the main driving factors to decide which final moisture content we need. But in fact, it's not the moisture content. In fact, it's the water activity of the product, because bacteria need access to water. This is the main restricting parameter for microbes, to get water from a product, and those are dried products, and so it's difficult for microbes to get water from it. And we call this the water activity of a product, and this is here the water vapor partial pressure in relation to the water vapor saturation pressure. Exactly what we have had yesterday. Nothing else but relative humidity. Same principle here. Yeah, yesterday we had a W here and here WS to remind. Yeah, and this is the relative humidity divided by 100, because this is here just the relation, dimensionless. And this is the water activity, AW value. And this is introduced worldwide, the water activity AW. And this is nothing else than the relative humidity in the product. imagine a grain storage or a bag of grain, and in this bag of grain there are pores, of course, inside, air pores, and this is the relative humidity inside this pore volume. And this humidity is in exchange with our dried product. The two things, the air in the pore volume and our kernels, they are in equilibrium. And now, this story here. We have here now the water activity from 0 to 1 or from 0 to 100% when you would like to express it in relative humidity. That's also common, either using water activity AW or relative humidity. And we see here the other axis, the moisture content of a product, and then you see here this fat line. And this fat line here, this is the equilibrium between the moisture content of the product and this water activity. And then we see here also other curves. The intensity of growth of bacteria, yeast, mold, here the enzyme activity of the product, here the non-enzymatic browning reactions of a product, and then we have also fat oxidation of a product. You see funny curves, and all of them are depending on the water activity of a product. And for us, they are very important here, the growth of mold, yeast, and bacteria. And you see it starts at 0.7 here and then goes up tremendously. If you exceed a bit the 0.7, then you have an explosion of the microbes. Then they have access to water. Yeah, then the water activity of the product is high enough that the molds can extract water from the air for living. Okay, but I would say to be on the safe side, we recommend 0.6. Yeah, to be on the safe side. Better to be here on 0.6 because then also the enzyme activity is reduced. You see, enzyme activity is also growing here. Okay, and fat oxidation, this is a matter here of oil crops like rapeseed and so on. And they are also dry down commonly to a lower water activity to reduce here the fat oxidation, which has a minimum here. Okay, but now to the sorption isotherm. What does it mean? If I need 0.6 of water activity or maximum 60% of relative humidity in my pore volume, then I go up to my curve and I go to the left and I can read here the required moisture content. Okay. This is the importance of this curve, and it is called isotherm because this curve is valid for one certain temperature. Let it be 20 degrees, and you need the other curves for higher and for lower temperatures. So this is just the general structure of an sorption isotherm. I think all those things here you can read through. I will explain all these things when we come to the curves here. Like this. Now we go to the curves. I have here a nice one here, such a blue one. Special S shape, which is characteristic here for sorption isotherms. We have here relative humidity, here our 60%, and we have here the moisture content here in wet base here. I have a line with 15% in my example, and I brought along here a sorption isotherm for 20 degree centigrade. Okay, now what is the equilibrium moisture content now of a product? Imagine that we have here a dryer, simple dryer here. Here is the grain, and here an airflow is pushed through it. Yeah, okay. And this airflow might have a temperature of 20 degrees and 60%. Ambient air in Germany. Okay, pushing air through it. And this was wet at the beginning here, and this will now dry down. And after a while, you have reached equilibrium. Yeah? And then you can find it, 60%. and 20 degree. This is a line for 20 degree, okay. And then our equilibrium would be 15%. Okay. That means if I'm sure that my air always has this condition here, then 15% would be sufficient. I'm on the safe side. Yeah, I have here 60%. Okay. EMC, equilibrium, moisture content. You remember, this is this one. Being in equilibrium with those air conditions. Also found here, 20 degree, and 60% humidity. So if now our product here has a higher moisture content, typically when coming from the field, then we have here desorption. Okay, going down to this point and then it remains. There is equilibrium. You cannot try deeper down the cereal with this air. Not possible. Stops here. On the other hand, if you have dried the grain at higher temperatures, deeper down, maybe even in the oven, more than 100 degree, bone dry, and you bring it in such a situation, airflow over the product, much air over the product, and then the product would absorb water until coming to this point, and then it's in equilibrium. When using these air conditions. Okay, so you now know about desorption and adsorption. Good. So now we also have the term equilibrium relative humidity, EHR, same chart, but now we have here a closed system. In our example, closed system here, we have inside our cereals at a certain moisture content, in our example, 15% here. And what will happen inside might be a bag, airtight bag or box, cereal inside, no exchange of air, certain pore volume inside. What will happen? Here, if the relative humidity of the air has been low at the beginning, here 30%, then it will rise. That means some water will come out here from the material here, and the relative humidity is rising to this point. Here we are reaching the curve, here we are in equilibrium. What would happen when the surrounding air was humid, like here in Costa Rica? Okay, then inside the system here, the relative humidity will decrease until reaching this point. Okay. Now I have told you that you need a curve for each and every temperature. And the one above here, the dark one, was 20. The next one is for 30. The next one is for 40 degrees centigrade. The higher the temperature, the lower is the position of the curve. Keep this in mind. 20, 30, 40 degrees centigrade. Okay, let's look at such a system. Closed system, typical for storage, okay. Grain in a bag or in a container, okay. And we have done everything well. We have dried it down to 15%. And you see for 20 degrees centigrade, this is my 20 degrees centigrade line, everything is fine. We are here at 60% relative humidity, and we are not in this gray, dangerous area where microbes might grow. Everything fine. So, but now we bring this container to Costa Rica. Down there at the coast, maybe some days having here 40 degrees centigrade, maybe somewhere in the harbor. What is happening in such a container? So temperature is increasing, maybe to 40% in this container, and then we are on this curve. This curve is for 40 degree centigrade. And then you see, oh, now we are slightly above 70% relative humidity in this container. Just because the product here is releasing water and the humidity in the pore volume is increasing. So luckily cereal is a good heat insulator. It takes time until the temperature is penetrating the entire bulk. But if you wait long enough, if you have this container for some days and weeks in the harbor, in the open sun, then this might happen. And therefore, the recommendation is not 15, but it's 14, yeah, to be on the safe side. Yeah, yeah, and that this can happen here, you see, if I go here to the right, if I moisten the air, then also the moisture content of the cereal goes down, but this is negligible. You cannot measure it, and I can show you why. So if we calculate the water in this grain bulk, yeah, in my 1 cubic meter box of grain here at a moisture content of 14% wet base, 1 cubic meter, then I have a bulk density of 700 kilogram per cubic meter, by the way. Yeah, so this cube is lighter than water, not a ton, but 700 kilogram per cubic meter. And I have a relative pore volume of 0.34. That means 34% of this volume is air in this container. Between the seeds are pores. And then we have here a mass of water in the grain left here of 98 kilogram. In this cube of grain, we have 98 kilogram of water in the grains still, because they have 14% moisture content. There is some rest of water left. Okay. What about the air in the pore volume? So we have here a specific humidity of air of 8 gram per kilogram in my example. You have more here, you have 14. An air density of 1.2 kilogram per cubic meter. The same pore volume of air, of course. And then we have here a mass of water of 0.003 kilogram in this air. And if you now make the ratio, turn this round, air to grain, it's 1 to 33,000. There is so much more water in the grain than in the air that you don't feel it in the moisture content of the grain. Yeah, this small amount which is necessary to rise the relative humidity in the air is so tiny, that you cannot measure it. But the moisture content of the air is so decisive for microbial growth. A little bit more water in the air, and then they can grow. Okay, and now to make it a bit more complicated, there is a small difference between desorption and absorption. So we distinct between desorption isotherms and adsorption isotherms, and we see it here. Again, we have a system, an open system, where we are pushing air through. We have our desorption isotherm and our adsorption isotherm. So if we have a wet product, it goes down here until meeting here the desorption isotherm. If we have a very dry product, then it's remoistened until reaching the adsorption isotherm. So there remains a rest in between, which is called hysteresis. I would say this is a bit academic, but you will find it in most of the publications, the distinction, and therefore we have to deal with it. I call it academic because it's not so much as we see it here in this schematic drawing. The difference is not so tremendously big. And I would say in many studies, if they would have waited longer with their measurements, maybe they even would have come closer, because equilibrium is a thing of eternity. You have to wait infinite time. Yeah? Normally, nobody can wait infinite time. Our life is too short. So that means, okay, waiting longer, maybe you come closer. Nevertheless, there is this distinction, and if we look it from the side here of a closed system here, what does it mean? If we have first a very dry air, so it will take up water coming here, and if you would have a very humid air, the air relative humidity will go down until this point. Okay, now how to measure sorption isotherms. So there are two principal methods. Yeah, we would like to have here points in this chart to draw through our nice S-shaped sorption isotherm. So there is one philosophy that we set a system here which has a certain temperature, let's say 20 degrees, and which has here a relative humidity of 10% or 25 or 40 or 70 or whatsoever. And then bringing the seeds in, yeah, for the desorption isotherm, we would bring in here humid seeds, and then the moisture content would go down and stop at equilibrium. Stop here, stop here, stop here, stop here, stop here. And then we can draw a line through. And this is the most ancient method and still used. And it's done like this. There are vessels here, and here are different salt dilutions. And according to the kind of salt you use, you have a certain relative humidity above this saturated salt dilution. You keep this in a climate chamber. You see this here, the roast of a climate chamber, keeping at 20 degrees. And then later on, the system with 30, 40, and so on degree. And you have here a small vessel here, and you put the material inside. You open it, you close here, and then the system will get into equilibrium. You have to wait for days. Yeah, you see it also schematically. Here the saline solution here, our sample holder here, the sample inside here, and the lid. Why the lid? When you now, for measurement, open it, you quickly close the lid that no water is exchanged, and then you bring it to the balance and you take the measurement and you bring it back again. This is a typical task for bachelor students. So you can do it really for hours and days to do this. Okay, here are different salts. For example, here this K2SO4. Here has a very high relative humidity in the headspace. Yeah, this is not very hygroscopic, this salt. Very good to know, here is sodium, NaCl, and this is around 75. Depending on temperature, those are also sorption isotherms. Here 25, 50, 70 degrees centigrade, and we have here our values. For calibrating a sensor, you can take just sodium, saturated solution here, bring your sensor inside, close it, bring it to a certain temperature, 20 degrees, and then you can wait if your sensor is showing here the 75%. Or here lithium bromide, which is very much hygroscopic here, very low relative humidity in the headspace, and these are my lines here. Yeah? System 1, 2, 3, 4, each are other salt solution. Okay, you see this is very time consuming, and that's not only a problem of labor, but also your material is going to rot. If you have it here at a high humidity here, yeah, for days, it will rot, and therefore you have also to disinfect it before here, and also adding here some toluol in the system. Do everything to prevent the rotting of the material. Okay. The other way is here, the other way around. Okay. I dry my material, some samples to 25 to 20 to, I don't know, 4. moisture content, and then I bring it in a chamber and I measure the relative humidity. Yeah, I look, okay, I stop here for the dry sample, I stop here for the medium dry, I stop here for the next, I stop here for the wet sample, and I can draw my line through it. This is also done. You see here the lab setup here. We have here these small chambers. This is a chamber, this is a chamber, and there's a water bath to keep the temperature constant. And you put the material inside in the sample holder, and then you close it with the sensor system. The sensor and the little ventilator are integrated here, and then the relative humidity in the system is measured. So in this case, the air is reacting. In the first case, the material moisture content was reacting. Okay, so now I have to jump back again. If I have my data points here, then it would be nice to have such a smooth curve through it, and there are certain models, equations. And there are more than 50 in the scientific market, but I have brought along here 3 very frequently used ones. Here the modified Henderson equation, MHEE, and we go to one of them. We see here the relative humidity. This is this axis here in the equation, and we see the moisture content in the equation. This is this axis. This is in the form that relative humidity is given as a function of moisture content. You also can easily convert it. Just convert the equation, and then you have it the other way around. And we have some things more, and one is the temperature, because we have isotherms. And by different temperatures here, we are producing here the different lines. What else do we have? C1, C2, C3, and those are the coefficients. Those are the adjustment screws. So a computer program is turning the screws to fit the model to the data points, so that the difference between the data points and the curves are minimum. The sum of deviations is minimized by iterations. So changing C1, changing C2, changing C3 until the deviation is minimum. This is done by computers meanwhile. Very smooth. The modified Chang post has the same principle, but a bit slightly structure of the equation. The same is true for the Oswin equation. All of them have 3 parameters, 3 coefficients here. They have temperature, and they show relative humidity as a function of moisture content. We will use those models in our practical today. So, here you see some data points here, and how here the lines have been then put through it. We have seen this. And here you see how long it takes here. So you have to wait here for, I would say, 40, 50 days until you have equilibrium. This is really long to wait. For this point, it's quicker here. You reach the equilibrium here after 10 days. But you can imagine what happens when you keep this in this high water activity here for 50 days. And therefore we have developed a better system in Hohenheim. So we are using a climate chamber. This is a climate chamber here, and inside the climate chamber you see those sample holders, and they are connected with balances. 5 samples connected with balances on top of the climate chamber. And in the climate chamber here we can keep constant the temperature, and we can change relative humidity. We don't need the salt solutions any longer, and we have a ventilator inside who is agitating the air, so there is a much better exchange between air and sample then in such a vessel, which we have seen the classical method. And we call it the dynamic wave absorption method. You see here Hohenheim, you see here this climate chamber here, and on top you see the balances, better here from the top view. Those are the 5 balances here of the sorption isotherm machine. And you see what is then measured. Yeah, the blue line here is the stepwise increase in the system, stepwise increase of the relative humidity. And the red one is the weight of the sample. Yeah, and the weight is proportional to the moisture content. The weight here is increasing step by step because the material is absorbing water from the surrounding, getting heavier. And the nice thing is we can, of course, watch the curves, or a computer is watching the curve. And when here equilibrium is reached here, then the system is switched to the next humidity, going up, going up, going up. So, and then always here we have a measurement point. You see here the measurement points. And we replicate it. Yeah, we have 5 samples at the same time, and therefore you see here also deviation. And interestingly, the deviation is more and more increasing here. You see here, we have a very high deviation here when it comes to very high humidities and moisture contents of the product. But very reliable here in this region, which is decisive, yeah, around 60 here, it's the interesting zone here. And that's the way how we can measure sorption isotherms in a very good way in our lab in Hohenheim. This here, by the way, are the absorption isotherms, and we also can do it for the desorption isotherms, just starting high up, yeah, with a high moisture content and then going stepwise down. Yeah, that's the same. We're just showing here this point here is later on the mass is converted here to moisture content, and then we have the point on the line. And the effect of temperature, this was for 25 degrees and this for 45, and you see here the difference was not tremendously big. Yeah, and then the isosteric heat absorption goes a bit far. Maybe you remember here the evaporation heat of water was 2,500 at 0 degree or 2,385 kilojoule per kilogram at 50 degree. And when we remove water from a product, this heat is higher. This is what we see here. This is the isosteric heat absorption. And if we go here to 50 degrees centigrade, then we see that instead of 2,385, depending on moisture content, when the product is getting more and more dry, is here reaching even 2,600. Takes more and more energy to remove the water from the product. The drier it is, the drier it is. Here is the moisture content in dry base going down here, and the isosteric heat is increasing and is higher for lower temperatures. And there is an effect of the product. It's different in between products. Yeah, we have here lemon balm on the bottom line, mushroom has a higher curve here, and papaya an even higher curve. And what does it say about the hygroscopic properties of the product? Which one is more hygroscopic? The lemon balm or the papaya? Which one is more hygroscopic? Keeping the water more. We have different curves. And we have also learned that this hygroscopicity is a function of the ingredients of a product. If there is sugar or starch or fiber. So which one of the three is more hygroscopic, papaya or lemon balm? Lemon balm is a herb. Melissa officinalis. Papaya, yes. Papaya is more hygroscopic and it's logic. There is more sugar, yeah, than mushroom and here this herb, lemon balm. Yeah, and if you now have to know the moisture content, then you go to 0.6, you go to the curve, you go to the left and you see what you need. Yeah. Here it's in dry base, so you have to convert into wet base to give this information to the farmers. And there is even a difference in between the plant organs. We have here such a nice lemon balm, Melissa officinalis, and you see there is a difference even between the stem and the leaf. If you go deeper, of course, this is academic, because you cut it in pieces and you mix it and you have one product. But with our setup, we can measure stalks and leaves separately, because we can put low amount of sample in the sample holders. And then it's also a function how it is dried. Freeze-dried, air-dried, vacuum-dried, and you also see the structure. And this is a function of the structure. That was mentioned by you in the beginning, that this final moisture content also might be a function of structure. And you see it depends here on the structure. So if a product is freeze-dried, like this one, then the microstructures are still there, the small pores, which are now sucking water again. The fine capillars, they are not gone, they are not broken. They are still there by freeze-drying, in contrast here to air drying. This is conventional convective air drying here, and you have destroyed some of the structure of the product. And this is the reason why we really have some effect of hysteresis. You remember I told you this difference between absorption and desorption, and that this is academic. Yeah, but there is a reason behind, because if you dry it first down, then you destroy structures, and if the moisture is absorbed again, it cannot reach the original state because the structures are not there. Some of the capillars have gone by drying. Yeah, this is also an effect on the isosteric heat. Good, not surprising, because this is a function of the sorption isotherm. And then we are ready for a break in a few minutes, but also to a few words to our practical, if you have no questions, but I assume that you have some, to what we have seen in the morning. Okay, not yet. Maybe we have done more when we work with it. I have just chosen a publication, one of thousands, about sorption isotherms. And I have here also uploaded this to the e-learning platform. And I have 5 copies for saving paper. Yesterday we had too much. Now we have more than expected students here. I'm very happy. But I think you can share, that every two can share one of these publications here. And this is about sorption isotherms, and there are those equations which we want to use. And the fine thing, there are also the coefficients, C1, C2, C3, which we need to fill the equations. And the interesting thing is that the author here just has collected what was already published about rice. It's a comparison of EMC, ERH, also equilibrium, moisture content, equilibrium relative humidity isotherms for rice. And he has calculated these coefficients for different models. And we take here the best model, and then we create our own sorption isotherms based on the equations we find in this paper. Okay. So then I would propose we look if coffee is prepared, and then we take a shot of coffee, and then we start to work. Thank you. strong enough to continue. You see on my back already the practical we will do, but maybe again some words here to sorption isotherms. We had an interesting discussion during coffee break. So that coffee now is traded by water activity and not longer by moisture content from some buyers, which is very good. But you have seen it's in fact the same by the sorption isotherm. The point in the sorption isotherm, a certain water activity is always related to a certain moisture content. But the factor for microbial growth is not the moisture content per se, but the water activity. So it's good to talk about the water activity, but farmers are not used to talk about water activity. But to measure it, it even would be more comfortable than in the moisture content in the oven method. So oven method, you know, you have to weigh in, to dry, to weigh out, to calculate. And if you want to measure water activity, you just can take a good moisture meter for relative humidity and put it deep inside the bulk of the coffee. And you will measure then inside the water activity. Very easy measurement. Yeah, we should a little bit think about that for the future. Yeah. You don't even have to do that. Because you know, when the water activity is below 65 or is 65, then you are safe. And this is what you want to know. If you want to convert this to moisture contents, then you have to know the temperature. But those sensors typically are measuring the temperature, relative humidity, and some also the pressure. And so even if you go down with a long rod in the coffee, by the pressure, you know where you are. They are so fine, I have tested it. The easily available sensors, meanwhile, like the one I have shown yesterday. Those ones, very handy. You have your access here, USB, even saving data. And you can measure here relative humidity, yeah, and you go down in the bulk, and it's also measuring the pressure, just ambient pressure. And if you go down, then the pressure is going up, and it's fine enough to measure 1 meter difference. So if you have a large store of coffee, and you bring it down in the coffee, you know point by point where you are and where you are reading the water activity. Just by pressing here the red button, you go here from signal to signal, starting with temperature. I would be happy to get it back again. Okay, so you see this knowledge is really exciting. And we can work on that in future with farmers, that we provide those measurement systems that they can measure the water activity of the product. And we also discussed it's a matter of the coffee itself. Nowadays we have coffee with mucilage around. It's fashionable to have also coffee with some of the mucilage, the honey, how do they call it? Honey coffee. And this has more sugar. The mucilage is full of sugar, and this coffee is more hygroscopic. And for the more hygroscopic coffee, you can allow a higher moisture content to have the same water activity. And this might be the reason why the buyers not longer ask for the moisture content, but directly for the water activity. Okay. So now to this paper about the sorption isotherms of rice. So this author collected a number of studies, 18 studies, and took the data from those studies and made the curves through the data points and provided this and looked for the best coefficients here. You will see this then on page 255. Could you download meanwhile the template and also the paper? So you have it also on screen, but I have 5 of the prints also with me. So there's also printout if you like paper. Who needs paper? Who likes paper? Okay. So Ashley likes paper. Okay, then there's one left for me, that's good. The sensor, thank you. So, okay, you see here, template. And I picked out here the data sets of the publication. And what do we see here? Rough and brown rice. What does it mean? Rough rice is rice where the husk is still around. And brown rice, there is the husk removed and still has the brown layer. And after polishing, it would be white rice. Okay. And then we see, for example, the first data set was rough rice, and they have data points from 0 to 30 degrees centigrade, and a range of humidity between 20 and 90. It was for desorption, yeah, DES. There have been 24 data points, and the study was here in the year 1948. And some data have been added then later on in 1960 somehow. Okay. Then, and they did here for rough rice and for brown rice, yeah? So this data set would be good to compare sorption isotherms between rough and brown rice. Yeah, and by the way, we now can think about what we would expect, what difference. Which sorption isotherm would be higher, the one for rough rice or the one for brown rice? Which is more hygroscopic, the brown rice or the rough rice? The brown rice more hygroscopic, why? Yes, more starch. And why has brown rice more starch than rough rice? Yes, the rough rice has still the husk, and the husk is fiber. And when the fiber is removed, the starch is relatively more. Okay, so we would expect that the sorption isotherm of the brown rice is higher than the rough rice. So then we have another studies here. Number 3 is just a study here on absorption. And then we have another pair, 4 and 5. No, it's not a pair. Interesting are always the pairs that we see what we can compare. I see 6 and 7 is a pair, same study, same orders, and we have here 40 data points for adsorption, and we have 32 points for desorption, and we have a range of temperature 27.5 to 32.5, and a range in humidity between 43 and 84. Okay, you see they are quite different. I look for more pairs. Here again I see 9 rough rice, 10 brown rice, and the same orders, same study, and the range 20 to 40 degree, and both are for desorption. Okay. So on the bottom line here, I see another pair, both rough rice, but one is a long variety, the other a medium variety, yeah, long corn or short corn. So here we could compare if we would like different rice varieties. Or if I go to 14, 13 and 14, here we could compare adsorption and desorption to find the hysteresis. Yeah, this is interesting for us. On the right, I show again the equations he used: modified Henderson, modified Jung-Fost, modified Oswin, and you will find the formulas also in the publication. Yeah, and here I propose some comparisons. Yeah, I prepared a scheme to fill in here the coefficients for the equations. You see here the name of the model, you see the number of the data set, and you see here what can be compared. If you want to compare rough rice and brown rice, we can take data set number 9 and number 10. I go up again. Yeah, that was here, number 9 and number 10. But it also would be possible to do it with number 1 and number 2. Also can be done to see a comparison. But by purpose, I have chosen 9 and 10. What do you think was my motivation to choose 9 and 10 instead of 1 and 2? Well, we can do both, but I decided no, let's take 9 and 10. Yeah. Temperature range for me even is strange, 0 to 30. What about absorption isotherm at 0 degrees centigrade? The cool storage for rice, or what? Who is storing rice at 0 degree? What else could be reasons? Because what? Year, yes. So an old study, 48. How did they measure in 48? Here I would say, okay, when they took the salt solutions, it was the same in that time. Having a good balance and having enough patience and time. Maybe they had more than we have today. Yeah, but okay, an old study, and then somehow combined. Yeah, he had combined data from 2 studies here to have these data points. I would say, oh, strange. Okay, fine. So 9 and 10. And then we can compare rough rice adsorption and desorption. And I proposed 13 and 14. Yeah, we have here adsorption, desorption. We have here a nice temperature range, 10 to 38. Yeah, and we have enough data points. Okay. And then I also prepared a comparison of temperatures. Yeah. I took again data set number 9 here 2 times, and I prepared here the system for 30 and for 40 degrees centigrade to see the influence of temperature on absorption isotherms. And then, yeah. And then the system is coming here. Yeah, in these fields we can program the model, and we are picking the coefficients and the temperature from above. Yeah, and then we can calculate here the relative humidity. Yeah, it's a bit the US system. Yeah, they are changing the axis, so be careful. We have then here our new y-axis, and this will be the x-axis. And the entry. We will see here the moisture content wet base, but the publication is based on dry base. And so we first have to convert wet base in dry base. I also put here the small equation which we need to calculate the dry base, moisture content. Yeah, and then I would say we can start. The question is how to select here the coefficients, and you should make your own selection, not just writing mine here. Yeah. And you can make your choice based on the publication. There are some means of quality which are also described in the publication on the page number 253. Yeah, the residual sum of squares, RSS, and so on. Error of estimate, SEE, or the mean relative deviation. Yeah. And if you go to the table of coefficients, you see the abbreviations of the models. You see the 3 parameters, or 4 for a model which we are not using. And then you see 3 columns for the quality parameters, quality of fit, how good is the model. And the smaller those quality parameters are, the better is the model. Yeah, and I like the MRD. I have focused on that. And then making a choice of the model. Yeah, so therefore I have here even different models. For comparing 13 and 14, I have chosen the Jungpost. Be careful. Yeah? If you want to compare your figures with mine, you should use here the same models, but if you select other ones, you are free, make your choice, but then you cannot compare with my data for check if your calculations are right. And also interesting, there are also some typos in this table, so don't believe everything you can read in publications. So if something is not working, then look at the coefficients. Yeah, sometimes a minus was too much or missing, things like that. Okay, I think now you have everything you need to work on your own computer and to fill in the system and to create these nice isotherms. By the way, I see here the first result already. The red curve for brown rice, the blue one for rough rice, and it's meeting our hypothesis. That was our hypothesis, that the brown rice will be higher, more hygroscopic, because less fiber. The husk is removed from the brown rice. Okay.